Welcome back, everybody. Here's just a review of the notes from Lesson 9-5. In this lesson, I introduced to you for the first time the standard form equation for an ellipse, and this is like Nortillo's version. If you look up standard form equation of ellipses online, or if you look them up in books, you'll usually find one or both, typically both of these standard forms. They change the A and the B, and I've told you about how I don't like that, changing the meanings of the A and the B or the relationship between the A and the B. I find that to be very confusing. I prefer just to go with this one standard form. As long as you know what all of the variables in this equation stand for, then remember, it doesn't matter what you call them. You can call them A and B one time, and then you can switch them to be B and A another time, and it won't matter because you know from the position in the equation what the thing stands for. But I think when you start out with these different standard form equations, then students get sucked into this trap of trying to memorize, well, this is what A stands for in this form, but then this is what B stands for in that way, and they get confused about which A stands for which in which situation, because they're not connecting the variables to any meaning. They're just memorizing a bunch of disconnected facts. So the way I've written the formula here, of course the H and the K are the coordinates of the center of the ellipse, just like they are for the circle. But what's underneath the x squared term is the radius in the x direction, always. That's why I like to call it r sub x squared rather than an a or a b. And what's underneath, or in the denominator of the y squared term, will always be the radius in the y direction. Sometimes the radius in the x direction will be larger than the radius in the y direction, such as the case with this ellipse here. The x radius is longer than the y radius, but sometimes the x radius will be shorter than the y radius. So sometimes the denominator under x will be smaller than the denominator under the y, and sometimes the denominator under the x term will be larger than the denominator under the y. Okay? But what's under the x is always the radius in the x. I think that makes so much sense that it's not hard to remember. Okay? Keep in mind that what is in the denominator is actually the square of the radius in the x direction, likewise for the y. So if you don't see a squared there, then this number 16 has already been squared from something else, right? This is a 4 squared. In this case, for this equation, the radius in the x direction would be 4. Now, if we wrote 16 squared, that would mean that the radius in the x direction was actually 16. Okay? Occasionally, students trip up over that. They get a little confused over that. I hope that you don't. The other key thing about ellipses is that there are these 3 distances which are always related to each other in this Pythagorean type of way. And again, I don't feel like you have to spend any effort memorizing this equation or this equation. None of the variables or what they stand for. I really don't think you have to invest 1 minute of time trying to learn those equations. Here's all that you need to learn. These 3 distances from the center are related in a Pythagorean type fashion, and the largest of the 3 is always the one that has to be by itself. Call it any variable you want. It doesn't matter. But clearly in this picture, the distance from the center to a vertex is larger than the distance from the center to a focus, and also larger than the distance from the center to a covertex. And that's the way it always is with ellipses. The distance to a vertex is always the largest distance of the 3. Foci, keep in mind, are always inside the ellipse. Foci are always inside, the ellipse. Okay? So, again, just a quick look at this one here. Right. Here's the largest distance. That's going to be by itself in the Pythagorean relationship. And here's the other two distances. Distance to a covertex, distance to a focus. Right? Technically, this is the vertex up here. In an ellipse, the vertices are always farthest away from the center of the ellipse. So in this ellipse, the vertices are up and down, above and below the center. And in this ellipse, the vertices are to the left and the right of the center, because this ellipse is wide and not tall. So anyway, just filling in some blanks here. Where's the center of the ellipse here? Just reading the graph, 5, 1. You know what? Next time I teach this course, although it's not inappropriate or incorrect for me to ask the length of the major radius here, I would kind of rather ask it this way. What is the x radius? Okay. I would prefer to describe this distance here as the x radius, because I want you to know that that number goes under the x squared term in the equation for this ellipse. Okay? It's not necessarily the major radius that goes under x. It's whatever the x radius is. Okay? So if you've got a copy of these notes, if you've got your own copy of these notes, maybe you want to do what I'm doing right here. Just cross out major. That's not wrong, but I prefer to think of this as the x radius so that we know where it goes in the standard form equation. And cross out this word minor here. What I'm really interested in is what is the y radius, the y direction radius of this ellipse. It's 3 units. So then the standard form equation becomes x minus 5, the 5 from here, squared, and the y minus 1 squared, the 1 is from here. And in the denominator under the x term, we put 4 squared. And in the denominator under the y term, we put the y radius squared, 3 squared, which is 9. You could write 4 squared here, you could write 3 squared here. I give you full credit for that. There's absolutely nothing wrong with that. Okay? And then we asked this question, which was not part of the handout per se, but I wanted to add it in class. Suppose now if I asked you if the point 2, 3 is on this ellipse, which, you know, it kind of looks like it is. Here's 2, 3. Wow, it sure looks like that ellipse might be going exactly through the point 2, 3, but maybe it's just getting super, super close. Like, how do we know for sure? Well, plug 2 and 3 in for x and y, and let's see what we get. When we plug those numbers in and do all the simplifying, you might need a calculator to do this, but you'd have a calculator available for you on any quiz or test on this unit. You'll find that 9/16 plus 4/9 does not come out to be exactly 1. Now, it does come out awfully close, but it's just not exact. So no, the point 2, 3 is not on this ellipse. If we want to find out the distance from the center to a focus, again, we know these 3 distances are related in this Pythagorean way. This 4 is the largest of these 3 distances. So it's going to go by itself in the Pythagorean equation here. The distance that we are missing, I like to call it f because it's the distance to a focus. But you call it a, call it b, call it x, call it anything you want, as long as you know that it stands for the distance from the center to one of those focal points. Solving for that f, we get about 2.6. So each focus has to be 2.6 units either to the left of 5, 1 or to the right of 5, 1. So if you start at 5 and you go 2.6 units to the left, 5 minus 2.6 gets you an x-coordinate of 2.4. So there's one focus at 2.4, 1. And the other focus, start at 5, 1 and add 2.6 units. 5 plus 2.6 is 7.6. Okay. On the back side, more the same. The ellipse is just turned the other way around. And again, I think it could be helpful here to change this to x. No, let's not call this. Here's what I'd like to do. Scratch this whole thing out. And let's write it. What is the x radius? And what is the y radius? I'm going to ask those questions in the same order. Okay. But the x radius turns out to be small this time, 2. And the y radius turns out to be larger this time, 4. So again, the x radius, that's what goes under the x term. Why isn't there a minus something here? Well, because the x-coordinate of the center of this ellipse is 0. The center of this ellipse is at 0, 1. You could write x minus 0 in parentheses, but really, come on, you're juniors and seniors in math. You shouldn't be doing that. I'm not going to take off credit for it, but you shouldn't be doing that. So it's just x squared over the x radius squared, 2 squared, which is 4, and then plus y minus 1, the minus 1 coming from here, squared over the y radius squared, 4 squared, equals 1. Always equals 1. Listen, when I ask you to write an equation, something that I will take off for, and people do this from time to time, is they'll give me the whole left side of the equation and they don't write equals 1. Okay, if you just give me that, it's not an equation, right? An equation has an equal sign in it. An equation has 2 sides to it. You can't leave out the equal sign and the whole other side of the equation. I've got to know that you know what it should be, okay? All right, and then again, finding the coordinates of the focus of each of the foci. We've got these 2 lengths already, 4 and 2. 4 is the largest of those 3 different distances, 1, 2, 3. So 4 is going to go by itself. F squared plus 2 squared equals 4 squared. Solving for f, it's about 3.5. So from 0, 1, if we go up 3.5 units and down 3.5 units. So starting from 0, 1, if we add 3.5 units to that 1, we'll get the coordinates of one focus. And if we subtract 3.5 units from that 1, we'll get the coordinates of the other focus. So here's the result when we subtract 3.5 units from 1, and here's the result when we add 3.5 units from that 1. Okay? That's all there is to these notes. Work through the 9-5 handout again. 2 days from now, I'll post 2 class days from now, I'll post the next video, and all we're going to do is review 9-6, just 1 lesson every 2 days. Take it nice and slow. And if and when we do return to class, again, we're going to hit the ground running with lesson 9-10, and I will expect you to be ready for that. Okay, good luck. Email me if you got any questions.